A nation's well-being and quality of life is heavily dependent on a secure infrastructure for controlling vital resources such as gas, water, and power. The Federal Energy Regulation Commission recently approved 8 security and critical infrastructure protection standards proposed by NERC in the wake of several security incidents threatening the reliability of the power grid. Utilities are under mounting pressure to comply to these standards, as it is becoming evident that the power industry's heavy dependence on increasing connected computer networks to operate their control systems is leading to vulnerabilities to well-known cyber attacks. Complexity and strong dependencies within control networks and operating procedures triggered due to faults or attacks make it very hard for red teams to do manual vulnerability assessment. Moreover, the NERC standards, while a major breakthrough on what security controls should be enforced, do not state how they be implemented. The evaluation team at TCEP is developing a toolchain to allow automated assessment of arbitrary control network configurations for compliance to NERC SIPs, security best practices, using technologies like first-order logic to model network entities, connectivity and logical dependencies, rewriting logic to model maintenance procedures for the power grid. It determines vulnerabilities to external attackers and ranks operating procedures according to their security risk. The toolchain automatically generates first-order logic predicates by parsing substation network schematics described in the Common Information Model, SIM, or the Substation Configuration Language, SCL, which are standards used by the power industry to exchange substation information. In a simple example to demonstrate our toolchain functionality, we work with a simple control network configuration previously imported from a SIM XML file. The windows on the right show how the various entities such as devices and services are described as prologue logical facts and their attributes, while security best practices are encoded as a set of rules applied to those facts. In addition, the tool allows the prologue to be imported as a graph. The window on the left shows a visualization of the same network diagram with solid black lines representing physical connections between devices and curved blue directed arrows showing service dependencies. Hovering the mouse over the devices describes the various properties and security attributes. For instance, we see that the admin PC supports a TLS stack. Devices may also be dragged elsewhere on the panel for better viewing. While the NERC SIP rules do not discuss implementation, various government security organizations such as National Institute of Standards and Technology NIST and the North American Electrical Reliability Corporation NERC have published a large amount of literature on implementing best security practices for control systems. The TCEP team has formalized these as logical rules allowing automated conformance checking of various control configurations. For instance, IONA's template for protocols access in industrial environments states that incoming DNS, HTTP, FTP, Telnet, SMTP traffic to the process control network should be discouraged unless absolutely required. Executing this query on our configuration shows an FTP service being hosted on a control device that violates this best practice. Similarly, the American Gas Association's report on cryptographic protection of SCADA communication states that in a proper access control implementation, the service should provide an authentication scheme and be capable of using protocols which guarantee confidentiality and integrity. Checking for conformance to this rule between all sensor and controller entities in our network shows 3 such paths, out of which 2 do not meet the criteria because of some intermediate hop, not supporting any security protocol. In yet another rule, that of checking against NERC's proper placement of firewalls criterion, the tool details which shared devices are properly placed behind DMZs and those that are isolated merely by packet filter routers or insecure application firewalls. For instance, in this case, the data historian, a shared device being accessed by machines in both the enterprise network as well as the process control network, is given a high security rating of 4 because it's determined to be isolated behind the DMZ. Other associations, such as that between the controller and the sensor, are given a lower rating because they are separated by just a stateless firewall. Maintenance and incidents recovery procedures performed by operators in the control centers play a major part in the proper functioning of the power grid. Further, knowledgeable and insider attackers, such as disgruntled employees, may use these dynamic properties to fake alarms, forcing operators to take actions with detrimental consequences. The TSEP team understands that relying on a security analysis of just the static design aspects such as the control network configurations may not be sufficient to ensure reliability of the power grid. Operational procedures are usually activities that the operators follow, for instance, to recover from a failed component or deal with some contingency. These procedures are made up of an ordered set of tasks that enable or disable control network devices. Tasks can be fulfilled in various ways, allowing operators a choice of strategies to perform a particular function. In this example, the tool chain passes a description of recovery procedure that an operator has to follow to bring up a transformer. The running of the workflow depends on the possible actions at any given task. For instance, the workflow task Select Transformer consists of two actions: Choose Transformer 2 and Choose Transformer 3. Depending on the current configuration, the task Transformer Grounded can either split to Ground Transformer or directly to Energize Transformer. Both splits and actions depend on the context, that is, which transformer was chosen earlier at Select Transformer, and whether according to the current configuration the transformer chosen was grounded or not. Given these workflow descriptions, the toolchain can model check them to verify if certain properties are satisfied. For instance, it can check to see if the final state is reachable from the initial state, i.e., there are no deadlocks, etc. In this particular scenario, we use model checking to rank recovery procedures according to security risk when a fault occurs in a substation, shown on the upper right-hand corner. A fault at the 77 kV bus bar causes the protection system to operate. Trip two of the transformers, TR2 and TR3, causing the remaining transformer to suffer from an overload. Operators in the control center have to reduce the load of the transformer in 10 minutes, otherwise TR1 overheats and burns out, causing a blackout of the entire substation. A subset of actions possible at any given task along with their given risks is calculated by the network analysis tool and is given in the table on the lower left. The security risk of a particular recovery procedure is calculated by aggregating the risks derived from all the vulnerabilities of each device used in the recovery procedure as obtained from the network model. This particular run searches for a workflow path that has a low availability risk. Essentially, we see that if we choose TR2, then we have a potential integrity risk because device DS8 has an integrity risk. That's shown in the diagram by red dots. Whereas if we choose the TR3, which doesn't have an integrity risk, but does have a potential availability risk because grounding the transformer uses switch NR3, which has an availability risk. Finally, the security model presents its evaluation of the possible recovery procedures to an operator along with the security risks.